Hi, in this lecture, I will discuss number systems. Number systems are important for us to understand because we, as a human being and as programmer, we think of numbers in the decimal number systems. So let me write that here. Decimal number system is the one that human being or programmer use. Whereas when it comes to computers, then in computers the numbers are represented in binary number system. So let's start the discussion with these two, decimal systems and binary systems. So even for understanding binary system, it will be good if we understand decimal system. Like how do we represent a number in decimal system, and if we are writing a number in decimal system, as an example, let me pick a decimal number 2375. This is in decimal. So if it is in decimal, then what does it mean? This is something we need to understand. And then later on we'll look at binary system, and then I will also use my lecture slides because the presentation in lecture slides is much better with some definitions, so that will make these things even better to understand. So in binary system we can have some other number. Let me put some number like 1011. So probably you won't be able to understand what this number is, 1011. This is in binary. Okay, so that's the point. For us, these binary numbers are not intuitive, whereas decimal numbers are intuitive to us. Okay, so we have to deal with the programmer, like we are programmers, and we think of numbers in decimal system, whereas computer stores the information in binary. Okay, so we need to have a good understanding of decimal systems and binary system. We will learn about how do we convert a number which is given in decimal to binary, and also if the number is given in binary, how do we convert that back to decimal. So these two are different numbers. This is 2375. This is in decimal, so we represent that like this, decimal. All right, this being in binary, I will write that with 2. Okay, so what's the difference? If you were wondering like how do we say that a number is in decimal system, or when should we say that the number is in binary system? So the difference lies in the concept of radix or base. So for decimal system has the base or the radix 10, whereas for binary this base is 2. We have other systems as well. We have octal, so let me put that right here. We have octal system also, there the base is 8. Then we have hexadecimal, their base is 16. So these different number systems that you are looking at, which are decimal, binary, octal and hexadecimal, so the main difference is the base. They have different base, and not only the base, they have different digits also. Okay, so these digits I will explain to you. Just hold on for a second. Okay, so now let me take this number which is 2375 and explain something to you. So that 2375, this is the number that I have in decimal. So we need to understand what does that mean. So it is 2375. So I can write that as 2000 plus 300 plus 70 plus 5. Okay, and I can rewrite it as 2 multiplied by 10 to the power 3 plus 3 multiplied by 10 to the power 2 plus 7 multiplied by 10 to the power 1 plus 5 multiplied by 10 to the power 0. Okay, so what did we do here? Let me write that as 10. Okay, that means I am representing it in decimal. So here, these things that you're looking at, 2, 3, 7 and 5. These are my digits. These are the digits in decimal system. Okay, and how about this? You have 10 to the power 3, then you have 10 to the power 2, 10 to the power 1 and 10 to the power 0. So here, if you're paying attention, I have the power of tens. Why do I have that? For the reason that my radix is 10. Okay, so the radix is 10, it's a decimal. So every digit is raised to the power of 10. And it depends like which position that digit is present in my number. So this digit 2 that you have is my fourth digit from the right. 1, 2, 3, 4. So what I'll do, I will have to raise 2. I'll have to multiply 2 to the power 2 by 10 raised to the power 3. Now the number digit 3 that I have in 2375 is in third position from right. So I'll multiply 3 into 10 to the power of 2, so on and so forth. Okay, so this understanding is important for us. And if you understand this thing, then understanding the other number system gets very easy. Alright, so this is 2375. Now let me add one more information, although I have that in my lecture slides. For decimal system, the digits which are allowed are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So these are the 10 digits which are allowed in decimal systems, starting from 0 till 9. Okay, so these are digits, and the base, you know, the base is 10. With this understanding, let's move on and try to understand binary numbers. So for that, what I should be doing, let me take this example which was 1011 in binary, and I'll tell you like what is that corresponding decimal number 1011 in binary. So let's start the discussion on binary. Maybe I'll use a new slide for that. Binary. Sorry about binary numbers. 1011. This is how I should express this fact that this is 1011 that you have is in binary, because see, I can also have 1011 in decimal, right? So this is different. This is in binary because I'm writing 2 here. This is not the same as 1011 10. These two are different because here the radix is 10, and here when I write 1011 radix 10, that means I'm referring to 1011 in decimal, but this is in binary, so this is different. Okay, so let's try to find out what a decimal number corresponds to 1011. So before we figure that out, let's try to interpret the binary number just the way we had done for this decimal number. Okay, so before we do that, let me tell you about the digits which are allowed in binary. So sorry, wait a second. See here, binary digits are 0 and 1, just 2. Okay, so that's the reason we call it binary digits, and this is also called as bit. What is this bit? Bit stands for binary digits, bits. So the only two digits which are possible in case of binary are 0 and 1. So you see here I have 1 and 0, 1 and 1. I do not have 2, 3, 4, 5. Okay, the way we can have in decimal, we can use all the digits starting from 0 till 9. There are 10 digits, that's the reason we call that as decimal. Here we have only 2 digits, so we call this binary. Okay, so now when we know that the digits which are allowed in binary are 0 and 1, 2, and we have learned about the decimal system, like how can we break the decimal number, and we can write 2375 as 2000 plus 300 plus 70 plus 5. Let's try to do the same thing on the binary. Okay, so how should I write this? 1011, which is in binary. Sorry about that, I have to erase this thing here. So it could be written as, let me start with the rightmost position. So this is 1. It is to be multiplied by, the base is 2 here. Okay, so in binary, base is 2. Binary digits are these two, and base is 2. It's not 10. In decimal we have base as 10, but in binary we have base as 2. So now right here I am referring to this bit. So here the digit is 1. 1 is to be multiplied by 2 because the base is 2. And what power this 2 should take? It's 1, 2, 3. So it will be 2 raised to the power 3 plus 0 multiplied by 2 raised to the power 2 plus 1 multiplied by 2 raised to the power 1 plus 1 multiplied by 2 raised to the power 0. Okay, so you should find that this is very similar to what we had done in the previous case, right? So in this previous case it was decimal number, so the base was 10. For 2 towards the digit which was the leftmost, we multiplied that by the base which was 10 raised to the power 3, because this is fourth one. Then 3 was the second digit from the left, we multiplied that into the base which is 10 to the power 2, and that's how we did for 7 into 10 to the power 1, 5 into 10 to the power 0. Now the same logic we have to apply, but now we are dealing with the binary. So the digits will change. The only digits we have here are 1 and 0. So when we wanted to find out the number that corresponds to 1011, so what we did, 1 into or multiplied by 2, which is the base in case of binary number, raised to the power 3. Okay, similarly, plus 0 multiplied by 2 square plus 1 multiplied by 2 plus 1 into 2 or 0. So let's simplify this and we'll get to know what number this represents. So this is 8 plus 0 plus 2 plus 1. Okay, so this number is basically 11 in decimal. So what did we learn? We learned that the number 11, which is in decimal, can be represented in binary as 1011. Okay, now you might be thinking that we somehow worked on a binary number and figured out the corresponding decimal number. How can we convert a decimal number to the binary? Well, that is possible. We can do that. But what I'll do right now is I'll take you to my lecture slides so that we are also covering some important contents, and then I'll come back and we'll work on some examples to understand the conversion from decimal to binary and decimal to octal as well, and we'll also look at other number representations, but I'll take you to my lecture slides. Okay, so here, as I told you, the important two things that we have to understand are decimal first and then the binary. So here in this slide, you're looking at the different digits which are possible in each number system. So binary has only two digits, 0 and 1. That's the reason we call it binary. Octal is another representation which has 8 digits possible. So octa means 8. So 0, 1, 2, 3, 4, 5, 6 and 7. These 8 digits are possible in octal system, and the base in octal system is 8, base or radix. In decimal system, which we know pretty well because this is the number system that we use in our day-to-day life, and so much so that even in programming, when we take an input from user, say the age of a person, then we usually take that as decimal. So the age of the person you might enter as 23 years. So 23 is decimal. So in decimal, the base is 10 and the digits allowed are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now the hexadecimal is the most interesting number system because here the base is 16. Octal has the base as 10, hexadecimal has the base as 16. So from binary to octal and then to decimal, you might have got this thing that the number of digits are related with the base. Binary had the base 2, so we had 2 digits, 0 and 1. Octal has base 8, so we had all these 8 digits, 0 to 7. Decimal has the base 10, so we have these 10 possible digits starting from 0 till 9. For hexadecimal, since the base is 16, we should have 16 digits, which is correct. Now, from 0 to 9, we have the same digits as we had in decimal. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now, the tricky thing is that how will you represent 11 as a digit? Because it has, if you want to represent that as using decimal, then you should have 1 and 1. Okay, so sorry, after 9 we have 10. So for 10, we don't use 10 as a digit because 10 has two digits, 1 and 0. So in hexadecimal, we have code for the 11th digit, 12th digit, 13th, 14th, 15th and 16th. So what are these codes? So after 9, we will use A for 10, B for 11, C for 12, D for 13, E for 14 and F for 15. Okay, so hexadecimal has these 16 digits starting from 0 till 9. These are 10, and then we have the remaining 6, which are A to F. F represents 15. So that's about the number systems and digits and their base. Now this is the point that I was discussing in that whiteboard. So why do we need to have a good understanding of number systems? Because we as human being and computer, we need to interact. Computer has its own way of storing data. So how does it store data? In the storage devices in terms of zeros and ones. That means in bits. Okay, so whereas we, human being, we like the numbers as decimal. Decimals are more intuitive to us than binary. Okay, so now one good thing about programming is that most of the times we don't need to worry about how to convert the number from decimal to binary and back from binary to decimal, because there are softwares which will do that for us. But here, since you're learning programming, you should know the logic behind it. Okay, so we should know that algorithm, we should know that approach which should be used in converting numbers from one number system to the other. Okay, great. So now again, what I was trying to explain to you using a whiteboard is nicely represented in this example. So this example is about decimal number system. So here we have these many digits. Let's look at this example. I don't want to read every line that you can do. So let's look at this number, which is 7423, which is in decimal. So what does it mean when you have 7423? That means the digit 3 that you have is at unit place, at ones place you can say, whereas 2 is at 10th place, 4 is at 100th place, and 7 is at 1000th place. Okay, so you can write this 7423 as 7 multiplied by 10 to the power 3 plus 4 multiplied by 10 square plus 2 multiplied by 10 plus 3 into 1, which is 10 to the power 0, which will give us 7423. Okay, so this understanding is important because the same understanding you can apply on other number systems to get the corresponding decimal numbers. That's what I did for binary example that I had 1011. So now here from this example you can see that the base is 10. So this base and radix is the same thing. Okay, so a number system is determined by the base that we use. Here we have decimal, so the base will be 10. Now the base of the binary number system is 2. I did explain, and the same has been mentioned here again, and it has 2 digits, zeros and ones. The base of hex number system is 16 because the hex system has 16 digits. Alright, now let's look at some example and try to understand that. You might be wondering that what was the need of having the number systems like octal and hexadecimal. We already had the decimal number systems which we people find intuitive, and then we have binary system which computer loves. The reason behind having other number systems, specifically hexadecimal, is that the hexadecimal number system is very compact, because if you look at the base, it has base 16. So with base as 16 you can write the number in a very compact way. Okay, so as an example, let's think about it. So right here, the example that you're looking at, so here if I ask you what is the number system here, you have 1010, 1010, 1010. So since the digits that you're using in this system or in this number are only 10, 10, 1 and zeros only, so probably it's a binary number system. Okay, it could be decimal as well, but I'll assume that this is binary. So if this is binary, then how can I represent this binary number in hexadecimal? So its corresponding hexadecimal has only 3 digits, which are A, and A. Okay, so look at it. Like you needed 12 digits to represent a binary number, which you can easily represent in 3 digits in hexadecimal. So the message is that the hexadecimal and the octal number systems are there to compress your binary number system. So they achieve the same thing, but you achieve better compression when you use octal or hexadecimal number. You can write the same binary number in less digits. Okay, great. So alright, so let's move on and see what do we have here. So the hexadecimal number system has 16 digits, which you already saw in the first slide. So since we have to represent these 16 digits, we are fine using 0 to 9, which are the first 10 digits from decimal system. But then we need to think about 11, 12, 13, 14 and 15. So for that, what has been done, we start with the capital letter A for 10, B for 11, C for 12, D for 13, E for 14 and F for 15. Okay, so that's what you have right here. Now with the octal number systems, we do not have any problem because the only digits that we need to represent are 0 to 7. These are the 8. So we are fine. Great. Let's move on. So now here we have a very general expression which says that how do we compute the value of a binary number in decimal. So here this slide is about the conversion of binary number to decimal. So which we did in the second example which I was working on, but let's do that systematically and try to understand this conversion from binary numbers to the decimals. So if you are given some binary number like B0, B1, B2 to Bn, that means there are n plus 1 digits in your binary number, then how can you convert that to decimal? Why is it n plus 1? Because see, you are starting from B0, you're going all the way to n, so n plus 1. So the same thing you can write by breaking it into the terms like Bn. What is B? B is the bit, I'll say, which can take value either 0 or 1, or you can also call that as binary digit or bit. Okay, so how do you write this? You will write that as Bn, which means the digit which I have at the nth position on the, which is the leftmost, multiplied by 2 to the power of n, okay, plus Bn minus 1 multiplied by 2 to the power n minus 1, and go on doing it. And every term is being multiplied by 2 to the power 1 less than what you had on the left hand side. It's left hand side, so you had 2 to the power n. Right here you have 2 to the power n minus 1, n minus 2. You go on doing it. 2 square 2 to the power 0. Okay, good. So now this is the general term which I believe you should understand and practice as well. If you're just reading it or listening to my video, probably that is not enough. You need to try it out. Write that on a piece of paper and figure it out. Make sure that you understand what we have written here. Good. So let's apply that to some binary numbers and try to get the corresponding decimal. So when you have 10 in binary, so there are only two terms, B0 and B1. So how do we do that? B0 and B1. These two terms only we need to be concerned about. So I have B0 as 0. So if you multiply 0 to anything, you'll get the result as 0. And B1 is 1 here. So 1 into 2 to the power 1. So you have 1 into 2 to the power 1 plus 0. So the answer is 2 in decimal. So if somebody is asking you how do you represent 2 in decimal, you have the answer here. It is 10. 10 is 2 in decimal. And you can get that once you put this in the expression right here, you'll get the corresponding decimal value. So how about 1010? Well, let's apply this expression on that. 0 multiplied by 2 to the power 0, which is a 0, plus 1 into 2 to the power 1 plus 0 into 2 square plus 1 into 2 to the power 3. Okay, so what's the result? This is 8 plus 2, which is 10. So 10 in decimal is represented as 1010. Okay, so I'll say that this if you understand this expression right here, then the conversion of the binary number to decimals is not difficult. So let's apply the same logic to this number, which is 10101011. This is in binary. So here you will start from, let's start from the right, that will be better. So you say 1 into 2 to the power 0, which is 1, so we have that term here, plus 1 into 2 to the power 1, so here B1 is 1. Okay, so that's what you have as the second term. And then the third term is a 0, so 0 into 2 square. Fourth term is 2 to the power 3, plus we have 1, plus fifth term is 0. Okay, so 0 into 2 to the power 4, plus sixth term is 1. Okay, so you have 1 into 2 to the power 5, and then you have seventh term is 0, and the eighth term is 1. So you have to ultimately add these numbers. So 2 to the power 7, this is 0, 2 to the power 5, which is 32. Then this is simple calculation, which will return the value as 171. So 171 in decimal is equivalent to 10101011 in binary. Okay, good. Now this is the tricky part. This is the other way around, which is like if we are given a number which is in decimal, how do we convert that to binary? So what I should be doing right now, let me take this example 123 and work it out. And when I work it out, probably you will see that better. And then we'll come back to this one and we will try to understand what we have here. So the number that I have is 123, which is decimal, and I want to convert 123 to binary. Okay, so let's see. So here, okay, so the task is we are doing decimal to decimal to binary. This is interesting. And the number that we have to convert is 123. 123 is in decimal, so I should write it like this. Okay, binary, we don't know. So let's do that. Now the algorithm or the approach is interesting actually. So it involves some mathematics, just the division. So let's work it out. 123. So what do we do? Since this is binary, we should divide it by 2. Okay, so when you divide it by 2, then this will go 6 times 12, then you get a 3, 1, 2, and your remainder is 1. Okay, 1 is your remainder. Now what should you do next? Let's take it out here, 61, and divide that by 2 again. So 2, 3 times 6, got 1, you will get 1 as the remainder. Okay, so this is 30 right here. I'll take 30. Let me divide 30 by 2 again. So you know 30, the remainder is 0. Okay, so let me do one thing actually. I don't want this 0 right here because this will create a problem later on. Okay, so I'll take 15 one more time and I'll divide that by 2. It goes 7 times 14, and you have this remainder as 1. Okay, let's take this 7 and do the same thing on 7 again. So you 6 times and you have this remainder. Alright, so since I'm running out of space, I'll take a turn upwards. So what should I do? Let's take this 3 and divide the 3 by 2 again. 2, 1 times 2, remainder is 1. Okay, now I'll take this 1 and I'll do the same thing on 1 also. 2, 1, this is 0 times 0, and your remainder is 1. Okay, so what did I do? Well, I started with the number which was 123, divided that by 2, and then I took note of the remainder, which was 1 here, and the quotient, which was 61. I'll take that 61 and we'll do the division one more time. Okay, so the result of the first division by 2 was 61 as the quotient and the remainder as 1. In the second step, I applied the same approach, which was divide 61 by 2, preserve the quotient and the remainder. And what will I do with the quotient? I will keep dividing the quotient by 2 and every time I should be storing the remainder. Now let me give some name to this remainder. I'll call that B0. What is B0? B0 is the first remainder that I got. My first division resulted in a remainder. I'll call that as B0. B1 would be my second last remainder. B2 this way. This is my B3. This being my B4. This is B5. And this is my B6. So what is my binary number? So the binary number that you get after this division would be B6, B5, B4, B3, B2, B1 and B0. That means what is B6? I have 1. Okay. B5 is 1. B4 is also 1. B3 is 1. B2 is 0. B1 is 1 and B0 is 1. Okay, so the binary number that I got for 123 is 1111011. Okay, so that's the process. Start with the number, keep on dividing by 2, preserve the remainder, and with the quotient that you got, you will do the next step. You will divide that quotient again by 2, and you will note the remainder, and whatever the quotient you get, you keep on doing it till the quotient is 0. Now since the quotient is 0, you cannot go any further. You have to stop. Okay, and then this sequence is also important. The last remainder that you have goes to the leftmost position, and the first remainder that you have is the rightmost. So this sequence is important. Okay, so let me see if I got the correct value. So these are initial 4 ones, then 0 and 1 1. So you have 1 2 3 4 ones, then 0 and 1 1. Great, so we got the correct values. So let me go over this slide. So again, you must have figured out that this is something where you need to calculate it yourself. So please do that exercise, and it's not difficult. It's probably the elementary mathematics. That's what you have to do, just division and remainder. So now, well, here we have some explanation which is trying to explain why are you able to get the corresponding binary number by doing these operations. It is up to you if you want to go understand this concept to that extent. I will say you are just fine if you know how to convert a decimal number to binary. So you should know this trick, or you should know this approach or algorithm or concept, whatever you call it. Okay, so what we did, one more time, let's do that. 123, divide that by 2, your quotient is 61, and in the process your remainder is 1. So this is much neat compared to what I did. It's a lot clean. So 61 was the quotient. You will do the next stage of division on 61. You have a remainder which is 1, but the quotient is 30. Let's do that again. You have 15 as the quotient, remainder as 0. We need to divide 15 by 2, quotient being 7, remainder is 1, and we keep on doing it, and we get the last case where the quotient was 0 and the remainder was 1, and the resultant binary is 1 1 1 1 0 1 1. Okay, so that's the way how we convert the decimal to binary. Now this is an interesting thing actually. We have the calculator. So calculator in Windows can be used to convert numbers from one system to other, the only thing that you need to do is you will have to choose the program. um, so let me do that. I know this is not very difficult, but let's do that. So when you go here and you say calculator, and you're looking at this calculator, right here you can change the calculator and you can go to programmer. Alright, so when you are at programmer, you can pick this decimal. So I will say decimal 123. I pick decimal, right? So when I type 123, which is in decimal, you can see the corresponding number representation numbers. So this 123 in binary is 01111011. So that's what we got. So if you have to convert that in octal, then the octal value would be 173. Decimal is 123 itself. For hex, it is 7b. So if you want to, if you're doing some exercises and you want to cross-check to make sure that you're doing it correctly, probably you can use this calculator. The only thing that you need to do is change the setting. Usually it is in standard mode, but here we'll have to go to the programmer mode. Right here you can see the different number systems. Alright, so that was about it. Okay, so now hexadecimal to decimal, this is interesting actually, but again, these are all conceptually the same. Alright, so conceptually these are the same. If you understand decimal, you can apply that to hexadecimal also. And you have already worked on binary. So the same concept applies to hexadecimal also, but now your base will not be 2. Your base will have to be 16 because it is hexadecimal. Alright, so here, look at this expression. If you have a hexadecimal number which is represented as H0, that means the digit that you have on the rightmost side, H1 is next to the right, H2, so on and so forth till Hn. So again, you have n plus 1 digits in your hexadecimal number. Now you want to find out the corresponding decimal representation. So how should we do it? Just the way we did in binary. But now that 2 is to be replaced by 16. So how do we treat the digit on the rightmost side? You'll say H0 multiplied by 16 raised to the power 0, which is 1, plus H1 into 16 to the power 1, plus H2 into 16 squared, so on and so forth. Alright, and then you'll have Hn into 16 to the power n. So this is the expression, which I believe is not difficult. You just need to try. If you don't try, it will be difficult. It's very simple, basic mathematics. Now, if you have 7f, and if you're wondering like what number system is that, so 7 and f, this f that you have here should give you a hint that we are referring to hexadecimal, because f is a digit which is only defined in hexadecimal. F does not exist in binary or octal or decimal. F only exists in hexadecimal and it stands for 15. Alright, so when you have to convert 7f to the corresponding decimal, what should you do? 15, f means 15 multiplied by 16 to the power 0, which is 1. So 15 plus 7 into 16. Alright, so you need to do this calculation, and when you do it, you'll get the corresponding number in decimal, which is 127. Okay, so here also if you're paying attention, then you'll figure out that 127 number in decimal needs 3 digits to represent it, 1, 2 and 7. Whereas if you convert that to the hexadecimal, then only 2 digits are fine, 7 and f. Why? Because the base is 16. Alright, so if you have a bigger base, if you have a higher radix, then you will achieve better compression. You'll have to use less number of digits to represent that number. If somebody is asking you that, F is my hexadecimal number, convert that to decimal. It's simple, right? F means that every digit that I have has the value of 15. So what do? I'll say 15 into 16 to the power 0 plus 15 into 16 plus 15 into 16 square plus 15 into 60 cube. So this can be computed. Alright, so you can make use of a calculator to multiply, and the answer would be 65535. So 1, 2, 3, 4, 5. So you needed 5 digits for decimal, whereas you will find with just 4 digits of hexadecimal. Now similarly, the octal numbers work the same way as the hexadecimals, but the base would be 8. Nice. Now, how should we convert decimal to hexadecimal? So we have already seen how to convert the decimal to binary. Okay, so same approach we have to apply for converting decimals to hexadecimal also. But now we will not divide by 2. We would rather divide by 16. So we have to divide by base. In binary we divided by 2 because the base was 2. In hexadecimal we have to do that division by 16 because our base is 16. Okay, so look at this approach. What are we doing? So for the same number which was 123, let's convert that to hexadecimal. So you will divide by 16. So when you divide by 16, so 7 times 16 is 112, remainder is 11. So you cannot divide 11 by 16. It has to be a remainder because 11 is less than 16. So what do? We keep 11 as our remainder, and we will try to divide 7 by 16. That will not happen because 7 is less than 16. So the quotient is 0 and the remainder is 7. Okay, and what's the corresponding hexadecimal number? It's 7 and the code for 11, which is, well, 10 was A, B, so it should be 7B. Alright, so 7B is the hexadecimal. Okay, good. Now, this is more interesting stuff. This is about hexadecimal and binary. So, let's look at this table right here. So we have decimal, hexadecimal, and binary. So 0 in binary is 0, in hex also it is 0. 1 in decimal is 1, in hex it is 1, in binary also it is 1. So that's an interesting case. Whereas 2 in decimal is 2, but in case of binary it is 1, 0. So you can convert that, right? Do that as an exercise. Convert 2 which is in decimal into binary and you'll figure out that it is 1, 0. Similarly, 3 is 1, 1. So 4 is 1, 0, 0 in binary, and see that till 9 hexadecimal and decimal numbers are same. Okay, but binary is changing. Why? Because in binary you can only represent 0 and 1 directly. For 2 it will be 1, 0. For 3 it is 1, 1. For 4 it is 1, 0, 0. 5 it is 1, 1. So for these things you'll have to do the calculation. Do some practice, and I believe you will love that. Now, what is the trick? Here we have a trick actually. So what's the trick? When you have to convert a hexadecimal to binary, how should you do that? Okay, so for that, let me take some example like 3, 8, and D. So we have okay, so what I'll do, let me work it out, right? Then I believe you will understand this better. So I'll try to memorize 3, 8, and D. So great. So what are we doing here? The task is to convert, sorry about that, hexadecimal, to binary. Oh, wait a minute. It was 3, 8, and D. 3, 8, and D. This is in my hexadecimal. I should write 16 here. I want to find out corresponding binary. So the trick is that, let's convert 3, 8 and D in binary. Okay, so 3 in binary is 1 and 1. Okay, so please do that as an exercise, right? Okay, so 3 in binary is, then 8 in binary is, this is 3, and 8 in binary is 8 in binary is equal to 1 0 0 0. This will 2 4 and 8. Now D in binary, what is D? So A was 10, B is 11, C is 12, D is 13. So we'll have to think about 13 in binary. So 13 in the binary should be 12 0 and 1. 8 19 11 12 13. Okay, so first you need to figure it out, do some practice so that you're able to convert these numbers like 3 8 and 13 in binary. So if you can do that in binary, then what's the trick? Like how can we convert a hexadecimal to binary? Well, once you have find it out, we will make these in 4 bits. So luckily 8 needs 4 bits, D needs these 4 digits, but 3 doesn't need 4 digits. So what we will do, we'll add 2 digits here. Alright, and what is the corresponding binary? The corresponding binary we'll have to write, like, let's put this thing which is 0 0 1 1, that was for 3, followed by 1 0 0 1000, which is for, it's not 1000, it is 1 0 0 0, sorry about that. Then you have 1 1 0 and 1. Okay, so this thing was for 3, this is for 8, and this is for D. 3 8 and D. Alright, so for hexadecimal to binary conversion is very simple. What you have to do is convert each digit that you have to corresponding 4-digit binary representation, and then put them next to each other. Alright, that's precisely what I did. I converted 3 in binary, which is just 1 and 1, but these are to be represented by 4 digits, so I'll put zeros on the left hand side. 8 I converted into binary, which is 1 0 0 0, and then D, which is 13, I converted 13 into binary, which is 1 1 0 1 8 19 11 12 13 13. Okay, alright, so that's the trick, how do we convert hexadecimal to binary. Alright, let's see if I got the same result. 1 0 1 0 1 1 0 1 0 1 3 0 1. Okay, yeah, we have the same value. Okay, so please do this exercise. So this lecture is actually more mathematical, I will say, but the only operations which we are doing are division, multiplication and addition. Alright, so whatever I have done in that whiteboard as an exercise is explained right here. To convert a binary number to hexadecimal, convert every 4 binary digits from left to right. Okay, and in the binary number into hexadecimal number, hexadecimal to binary. Now about octal and binary, it's the same thing, right? But now we will not consider 4 bits, we will consider 3 bits, because 2 to the power 3 is 8, whereas in hexadecimal 2 to the power 4 is 16. Okay, so the same concept will apply for octal to binary also, but here what we will be doing, we have to consider 3 positions at a time. To convert an octal number to a binary number, simply convert each digit in the octal number into 3-digit binary number. Okay, and then once you have done that, you need to combine that. So actually we have two processes here, how to convert the octal to binary and then the binary back to octal. Alright, so what do I have here? Here is an example of converting a binary to octal. So how do we convert a binary to octal? When this binary number is given to you, you need to start from right to left and make a group of 3. Alright, so from binary to octal, what we are doing, this is binary. Start from the right and make a group of 3 3 digits. So 101 is one group, 001 is the second one, 110 is the third one, and you have the lastmost one. And once you have grouped these, then we'll have to compute the corresponding octal. So 101 in octal is 5, 001 in octal is 1, 110 in octal is 6, 1 is 1 itself. Okay, so in the previous slide also, it has 2 parts. I explained to one which was converting hexadecimal to binary. Okay, so if you are given a binary, you can convert the binary to hexadecimal also, which is even simpler. So what you have to do, if this was the binary number given to me, alright, so how do I convert that to hexadecimal? I will group these binary numbers in the group of 4. So I'll start from right, 1011, that's 1. And then 1000, that's the second one. 11 is the third one. So once I have grouped these this binary number in the group of 4, I'll convert that group of 4 to the corresponding decimal. So here, if you convert this, then this will be 13. So that 13 in hexadecimal corresponds to the letter D. So I'll convert that to D. Whereas this 8 will remain as an 8 and this 3 is 3. So this binary number that you're looking at will be converted to the hexadecimal 38D. Okay. Alright, so this was it about the number systems. Number systems are very interesting, simple. You need to do some calculations, so please practice that. And since I did not cover that in your first midterm, so you should expect these questions in your second midterm and probably in your final also. And once you understand how we convert the numbers from one number system to the other, then you should start thinking about writing a program for doing it. Okay, so I'll discuss the program later, or probably I might discuss that in some review. But you should think about it. You should, once you understand how we are converting the numbers from one number system to the other, then you should think about writing the corresponding program. Thank you so much. Have a good one.